After doing the last lecture on transformations and rotation, I decided I probably ought to add this little lecture in here talking a little bit more about incremental rotation and how quaternions come in. Now, I labeling it as an optional lecture, but I certainly hope that especially all the graduate students uh, read this lecture video and especially the people who have taken 412. But actually, I think even for the rest of you, just going through it briefly will help you understand some of the issues that occur with applying transformations in WebGL or any other graphic system. So I want to do a couple of things here. What I want to do first is look at what direction angles are and Euler angles. I'm going to just go over very quickly a longer example that's in the book, which shows you how to do a general rotation by building up these smaller rotations about the x, y, and z axes, and then come back to the issue of what happens if you're doing a lot of little rotations to try and do things smoothly that are based on the Euler angles, and then we'll look a little more at quaternions, which we just said they exist last time, as an alternative to doing rotation matrices, and there's some very, very interesting things that arise with quaternions that I'll try and explain in this lecture. So, going back a little bit, there was a function in all of the fixed function pipeline OpenGLs called GL rotate that you gave it any direction you wanted and how many degrees you wanted to rotate about that angle, and it would do it. But as we saw last time, it's deprecated, and the primary reason is that that's a function that really only worked within the CPU. Now we put a rotate function into MVJS, which will allow you to do rotations in the application if you want to, or you can take some of that code and implement it in GLSL if you want. So there's a lot of things you can do with it. Now, all of that stuff is based on Euler angles, where we have a rotation about x, a rotation about y, and a rotation about z. The standard alternative to that is what are called the direction angles. So suppose I take a vector, and this is the vector I want to rotate by some angle theta, and how do I specify this vector? Although in principle I could say the way I get this vector, and this is what you would do if you were constructing an instance transformation, you would maybe start with it in some fixed position, say along the z-axis, and you'd figure out what were the right x, y, and z rotations to get it up in this position. But let's take a different view. Suppose I give you this vector and I specify it by its components alpha x, alpha y, and alpha z. And for convenience, let's assume we place this vector at the origin, so that if we start at the origin, then alpha x, alpha y, alpha z are the coordinates of this point. And then I could say, well, a different way of looking at this vector is to look at the angles it makes with the coordinate axes. So I could look at the angle. One way to do it is to project the tip of it onto the YZ plane, and then that will give me one of the angles projected down into the XZ plane. That'll give me another of the angles. But let's just say that we can specify it by these three angles, which are the angles that it makes with the X, Y, and Z axes. And in fact, I show you in the notes how to obtain those three angles from alpha X, alpha Y, alpha Z. And in fact, we do exactly that. First, just to summarize it very quickly, what we do is we normalize this. So remember, if I normalize a vector, it points in the same direction, but it has unit length. Then what I can do is rotate it down into the X plane. Actually, I should back up one step and say, if you normalize this vector, these three alphas have to have magnitude less than or equal to 1. And in fact, what they are the cosines of these direction angles. And so you have this very nice cosine rule, since this has to have length 1 because of the normalization, that cosine squared of the sum of theta x plus cosine squared theta y plus cosine squared theta z has to be equal to 1, and that's something that direction angles must obey. And it also sort of embedded in that is that if you know two of them, you'll know the third because the sum of the squares of the cosines have to equal to 1. So you could, given 2, you can solve for the third. Now, in terms of trying to figure out a rotation about this matrix, so suppose what I'm trying to do is rotate theta degrees about this axis specified by this alpha x, alpha y, alpha z. Well, one way to do that in terms of x, y, and z rotations is to first rotate about the x-axis until you rotate down into this plane. Now, the amount you have to rotate is going to define some angle theta x, not phi x as we have here. And the way you do that is you project this onto the YZ plane, and that angle you want to rotate down by is this angle, and that gives you theta x. Once you're down into this plane, now I could say, oh, what if I rotate by about y to align myself with the z-axis? And I could then figure out theta y from that, again in terms of alpha x, alpha y, and alpha z. Now my axis is aligned along the z-axis, and I know how to rotate about z by the angle that you've given me. So my third rotation is about z. That rotates my object, but I'm pointing in the wrong direction. So what I do is what I've done before, like with rotating about a fixed point, is I have to move myself back. So I undo the rotation about the y-axis to bring me back here. Then I rotate up to undo the rotation about the x-axis. So that's how you can go between Euler and direction angles. It also says that I've composed my rotation out of simple x, y, and z rotations that we've talked about, but there's, 7 of them here. And if the fixed point is off here somewhere, then I proceed it by moving the object to the origin with a translation, move the fixed point to the origin with a translation, and then at the end I move the fixed point back. And that's worked out in detail in the notes. So that's just sort of this whole approach by using Euler and direction angles. So we could do that, but it's a lot of work, and it's not particularly efficient, but is there a better way? And so that's what's going to get us into quaternions in a minute or two. First, I just want to go back and review what I said about incremental rotations. If you're doing a lot of rotations in an animation and you want to look at it to look smooth, now this notation is a little bit weird, but I'm saying the rotation matrix at time t, and then I want to know what's the rotation matrix at time t plus dt. Well, if I do very small rotations in the x, y, and z directions, I could get what the rotation is at time t plus dt. In other words, what we're saying is that the fact that the product of two rotation matrices is always going to be another rotation matrix perhaps about a different axis. So then I can go one step further and I could say, okay, what if these angles are very small, because I don't want to see the rotation about x followed by y followed by z to get me where I want to be. I want to do very small angles here for x, y, and z. Then if I do that, then I can say, well, why don't you use small angle approximations in the rotation matrices about the x, y, and z axis. So saying sine of theta for a small angle is about theta, and cosine theta is approximately equal to 1. If you do that for all three of these angles, theta x, theta y, and theta z, you can show that this product is approximately this very simple matrix with these thetas in it. Now we don't have any trigonometric functions here. That isn't perfect because and I'll leave this a little exercise for you. If you keep doing this with the same matrix, saying, well, I want to rotate and I'm going to do it in these little steps, but these thetas or increments are always the same. If you start looking at this matrix, it turns out you get a buildup of error. And the reason is that if I look at the determinant of this matrix, it's bigger than 1. So that says this matrix is, in some sense, getting bigger and bigger and bigger, while you can show very easily that for any rotation matrix, the determinant is 1, so they don't get any bigger. And you can try and correct that in various ways, but it's not a perfect solution to the problem. So let's look at the alternative. which comes from quaternions. And let me approach it in the following way. Suppose I'm on this sphere and I want to go from point A to point B. Well, we know that from flying that the route you take is not what it looks like on the standard two-dimensional map. What you're going to do is fly along a great circle that connects point A and point B. And the shortest path on a sphere is the great circle that's unique, that passes through these 2 points. Now, another way to look at it, which is a little less common, but what we want to look at is that this great circle determines a plane that has, the radius of the sphere, and that plane has a normal to it. If these points were positioned in different places, you'd see the tipping of this plane. So that in terms of this plane, to go from point A to point B, I'm doing a proper rotation about this vector that is normal to the plane. Now that's interesting, because now I've defined rotation by a single angle that has to do with this great circle, and not in terms of Euler angles or direction angles, which, if you look back to a principle that I'm trying to give you over and over again, because I think it's important, is whenever you work with a representation, you get a phenomenon called axis dependence. And in a way, using direction angles and Euler angles is coordinate system dependent, because it depends on where you decided to put your x, y, and z axes. This concept of the great circle is independent of any representation. And remember, we try to start geometry by saying, how far can we go without having a particular coordinate system or frame? Well, here's another way of looking at rotation through this analogy with moving between 2 points on a great circle. Now, how do we actually use that in practice? Well, here's a little review of what we just said. Shortest path is this on a sphere, is this great circle, and we're looking at this normal vector, and we can rotate about the normal vector. Well, quaternions, it turns out, do exactly that. What's called quaternion rotation is actually a rotation by theta about a certain vector. And so here in one slide is the quaternion math. You're better off, looking at the notes. But a quaternion, it consists of 2 parts. It takes 4 constants to specify a quaternion. The scalar part is this first component Q0, and then we can think of a vector that's composed of the other 3 components. So we write it as Q0 bold Q, where these are the components in these 3 imaginary directions. As last time we wrote it as I, J, and K. Now the arithmetic is kind of nice. Addition is what you would expect. You just add the corresponding components together. So if you have an A and a B, you add the 2 scalars for the first components, and for the second, third, and fourth, it's simply a vector sum of the 3 to get the 3 new components. Now, quaternion multiplication is more difficult. That the first component is A0 minus the dot product between A and B, which is a scalar, and the quaternion part of it, the vector part of it, it requires a cross product and a couple of more vector additions. Looks kind of arbitrary now, but what works out very nicely is its analogy with the sphere, and also with rotation. So let me give you a couple of special cases. The magnitude is, in some sense, the magnitude squared, in some senses, looks like the magnitude squared that we'd expect. The dot product is just Q1 squared plus Q2 squared plus Q3 squared, and the first component is you just square that. So the dot product is just like the dot product, or the magnitude squared is just like the dot product of these 4 element vector with itself. The inverse is interesting too. The inverse turns out to be 1 over this magnitude Q0 with minus of the vector part over here, and if you multiply it all out using this formula, that'll be true. Now, so far, you say, well, what in the world does this have to do with anything we're doing? Well, it turns out that if you say that these three vector components, Q1, Q2, Q3, represent a point, essentially they're the x, y, and z values, and you make the first component 0, then a rotation can be rep by theta degrees about this axis determined by this is using, it's half the angle. It's cosine theta over 2, cosine theta over 2 times the vector you want to rotate about. Okay, so if I want to rotate about a vector v by theta degrees, if I use this particular quaternion, then the rotation of this point P is given by the quaternion R times the quaternion P times the inverse of the quaternion R. Now, look, there's no reason for you to think, oh, that's obvious. It's not obvious. You have to work this all out algebraically to show that. But the advantage of this is, in fact, what you are doing is you can look at this as rotating about the great circle whose normal is v by theta degrees. So if you have a way of going between the normal representation in some sort of a rectilinear xyz space and the quaternion space, you have this very nice rotation. And we'll talk a little bit more about the mechanics in a minute. But this is the basic algebra of quaternions. You can also observe that because it's four-dimensional, you can say, well, what if I did these operations in a shader and used a vec4 to send a quaternion over to the shader, and then I could use a vec4 or vec3 to send a point over. In fact, that's really easy to do, and as I said in the previous lecture, the shader itself to do quaternion addition, multiplication, other operations is an incredibly simple little shader, and it might be some project or an exercise that some of you want to do. Now, let me look at the reason why quaternions are so important in computer graphics and other fields like aerospace and virtual reality. So let's look at what seemingly at first is a totally different problem, but it's going to point out the difference, the problems of using Euler angles and why we want to go to quaternions for certain applications. Okay, so suppose I have a sphere, and let's suppose this is the Earth, and I'm standing over here in the evening, and I'm looking at the North Star. So the North Star is directly over the North Pole. And I can say, well, I look at it, how do I say where the North Star is at this point on the surface of the Earth? Well, if I blow it up over here, this little area, I'm looking at the North Star, and I could say that the North Star is located at a certain elevation in azimuth. So the elevation, you could say, is the angle it makes above this little plane I make in the north, depending on the normal at this point I'm located at, and the azimuth is the angle in that plane that I've measured from some fixed location. So here I'm saying, oh, the fixed location is due east. So, and these two angles totally determine where the North Star is if I'm located at this point on the Earth. And that's sort of standard if you're in astronomy. If you're going to say, where do I point my telescope? You look up the elevation and the azimuth of each star at a certain time of night, and then you point your telescope in that direction. So that all looks fine, except there are singularities at the North and South Pole for the North Star. So, and I could show you it's exactly the same for any particular star. There's always going to be these singularities. And so look at what happens. Suppose I do the same thing. I go to the North Pole and I look at the North Star. Well, where is it going to be? It's going to be directly overhead. Okay, so here's a little picture of that. The North Star is directly overhead. And so what is its elevation? Well, its elevation is obviously 90 degrees up from this plane. Now, what is its azimuth? Azimuth in a sense is how I'm turning when I'm looking straight up. And the answer is, it doesn't matter, because no matter what I decide my azimuth is going to be at that point, I'm looking straight up. This is a real problem, and it's called gimbal lock. I'll talk a little bit more about that in a second, because now there's an ambiguity here on what the azimuth is. And the problem is I'm not sure quite what to do with my telescope at that point. And if I now start saying, well, how do I get to another point? Now there's confusion because I don't know what azimuth I'm really going to start with. So this is a serious problem, and it's come up in real life. I mean, what happened with what's called gimbal lock that arose in the aerospace community. This actually arose with some of the actual manned orbiters that they launched. I think it was a problem on one of the moon missions, is that they have gimbals, which are just allow you to have a three-dimensional axes essentially in there. And the problem is if you rotated one of those, there are three concentric rings that give you those directions. It turns out if you rotate one of them by 90 degrees, you've lost a degree of freedom. And what that means mathematically is if I just look at RZ, RY, RX, like we've been doing with Euler angles, and I say the Euler angle for Y is 90 degrees, the matrix reduces to this with a bunch of trigonometry, using a bunch of trigonometric identities. Now this is bad. One thing you've done is you've switched two axes by this one is over here. That's not an issue because that's just a naming thing of what you call the axes. The real problem is over here because what used to be sines and cosines of theta x and theta z are now the sines and cosines of the difference. So there's no uniqueness to what you get for a particular theta x and theta z. You could get the same thing with any pair of theta x's and theta z's whose difference is the same. And that's removed a degree of freedom. It totally screws up the guidance system if that ever happens. So if a guidance system ever got into that situation, it had a problem, and that arose with NASA. The story I've always heard about this, and you can look this stuff up on Wikipedia, it's not a bad discussion, is that one of the proposals was to put a fourth direction in there, and so if you had a singularity in 3 dimensions, you wouldn't have it. You could always bring in the fourth one, but they didn't want to do that because of the weight until they actually got into this problem. So what happened is in both in aerospace and computer graphics is somehow they rediscovered quaternions, which had been discovered by the math community, and that has a very long and interesting history behind it. And the aerospace community said, oh, here's some mathematics that will cure our problem if we work with quaternions instead of working with Euler angles. The same thing happened in the animation community quite a while ago because they were trying to get smooth rotations as a camera moved through the scene, usually a virtual camera. The same problem arises in virtual reality, and this is closer to what was done in the aerospace community, is if you have a head-mounted display or virtual reality or augmented reality, you get into exactly the same problem of what happens when your operator with a head-mounted display is rotating his head about his neck. So all of these things are important, and people now routinely use quaternions. I mean, I have a lot of people who have used my book that say, I won't use the new edition unless you have quaternions in it. That's really the key thing. But the mathematics is not simple, but they at least want you to get a feeling that there is another way to do this that solves some of the problems. But it doesn't solve all of the problems. And one of them is that if you do rotation about x, rotation about y, rotation about z, it's very easy to keep the up direction. So imagine that you're moving a camera around some path and you're making a movie, either a real movie or an animation. You generally want the up direction to remain unchanged. It turns out if you do quaternions, it doesn't have any reason to preserve that direction because doesn't have any underlying frame in it, and so it doesn't preserve that up direction. So even though you get a smooth motion along the trajectory that you're trying to go along, that your camera can have its up direction moving, and that can be kind of annoying. But in fact, they are used very routinely. Okay, so working with quaternions, I think the key thing is that the shaders are very, very simple. to do, and I'd really think it would be a very good exercise to go and write yourself a little quaternion shader. Have a function that does quaternion addition, a function that does quaternion multiplication. In GLSL, you not only can have mains for your vertex shader and your a fragment shader, but you can also have functions in there. So you can define a trackball multiplication function and a trackball addition function, and and write some code using that. Now, there's no simple way to go back and forth, unfortunately, between matrices and quaternions. There is a mathematical way of doing it. It's moderately sophisticated math to do that. Generally, what happens is that because you're doing translations and scalings and other types of transformations, not just rotations, all that quaternions are good for is the rotation part. So generally what people do when they use quaternions is they take the matrix form that we've been using with the Euler angles, and they copy the sines and the cosines into the proper places to get a quaternion. Then they manipulate with the quaternions to do their rotations, and then they copy the elements back into the standard matrix form. And generally, that's the best you can do. And the final thing is, not only are the quaternion shaders simple, if you count up the number of operations you have to do a rotation by quaternions, or to do a rotation by Euler angles, x, y, and z rotations, in fact, the quaternion rotation is more efficient.